welcome to the concepts video on vectors in 3 dimensions. Okay, so the first thing I want to start with is kind of more or less like, it might or might not be a Thursday right now when you're watching this video, but we're kind of going to do a throwback anyways to maybe something that you learned in Algebra 2, in an Algebra 2 class in the past. We're going to start with the distance formula. Okay, so in 2 dimensions, because there are a couple cases here, so 2-dimensional case is the following. So we have, like, let's say a point P, which is A1, B1, and Q is A2 and B2. Okay, so those are our coordinates. So to find the distance, what you would do is just take the difference between the x coordinates. So we're going to do A2 minus A1, square that value. We're going to do the same thing with the y coordinates, b2 minus b1, square that value, add them together, and take the square root. Okay? And now I'll just show you in the 3-dimensional case, you might or might not have seen this already. Going back. So this distance is basically just saying the difference between P and Q. Distance here. So the value when you subtract the points. Okay, so now in the 3-dimensional case, we'll have something very similar in structure and everything, but just now we have 3 components instead because we're dealing with 3 different dimensions. So then we have R and S, let's say, and A2, B2, and C2 now. Okay, so that's our Z component, and we're basically going to have the same exact thing. So D, the distance between R and S, is going to equal, we're going to find the difference between all of the components respectively, so B2 minus B1 squared, C2 minus C1 squared, addition sign in between there, and we have our square root sign. Handy dandy, right? Okay, so just wanted to introduce that as something you might have seen before, and we'll take this bottom one here and we're going to kind of expand it into the next topic. All right? So I'll rewrite that up here. So we have D equals R minus S, the distance between the points in 3 dimensions. So again, that's going to be this actually. Okay, so I'll rewrite it a little bit. Let's say that we don't have, hold on, let me go back here. So let's say we're finding the distance between some other point, not R, but P minus S, okay? And let's say P has some coordinates X, Y, and Z, or something. And then we have S being our, like, A, B, C. Okay, so we're just going to find the distance between them. So we're going to do, let's say, X minus A squared plus Y minus B squared plus Z minus C squared. Okay, and then all, again, under the square root sign here. And I should note that inside, it doesn't matter whether you do X minus A or A minus X because it's just going to be squared anyways. So if you get a negative sign, it'll just come out as the positive value. Okay, so pictorially, what this looks like is that if you're finding the distance, let's say, okay, so we have our 3-dimensional case. So this is our x-axis, y-axis, and z-axis. Okay, so let's say our P, let's say that is right. Well, let's say S is here. Okay, so here's our point S. That's A, B, C. Those are our coordinates, right? And then P is somewhere else. It's floating around somewhere. So since I named it X, Y, Z, that means that it could be anything, right? So any point, and I'm just drawing a circle here, kind of hinting at something, right? So we'll have P be like right here, okay? So let's say P is X, Y, Z, all right? So that's just telling you this is the distance here between these 2 points. That's how you get D, okay? So let's say P were over here or something. All right, and it was still X, Y, Z, some X, Y, Z coordinates, and this was the same distance, okay? So what we actually have is no matter where you move, if this is the same distance, then we actually have a radius going on, right? So our distance is the radius of a sphere if the distance between 2 points is the same. If this S is stationary, it doesn't move, okay? This will be the center of your circle, and any other point that is the same distance away okay, same distance away from this S, that's going to be on the surface of your sphere, okay? So S is going to be the center. So this is the center of our sphere. And P, which is given by x, y, z, is any point on the sphere. There we go. Okay, so we're going to take this, and like I said, the distance now, since we're considering a sphere, is now, it could be considered the radius. Okay, so radius. There we go. So now I'm going to kind of rephrase it a little bit, just change the equation a little bit, and we're going to square both sides. Okay, square the left side and square the right side. So on the left side, we'll have radius squared, and all of that squared is now equal to, so the squared exponent here and the square root sign cancel. Okay, so those cancel, and we just get x minus a squared plus y minus b squared plus z minus c squared. Okay, ignore this little x thing. Sorry if that got in the way there. But this is basically the equation of a sphere. Okay, and sometimes the left side is just denoted by like capital R squared for radius. So this is the equation of a sphere. All right, where I should note that ABC, this point here in space, is the center. All right. Okay. So now, so we dealt with the sphere here, and then let's say. So we have our equation for the sphere. So r squared equals x minus a squared plus y minus b squared plus z minus c squared. So this is our equation for the sphere. But what happens if we drop the z component entirely? Okay, so if we cross that out and we kind of just like, it disappears into thin air, what this means is that this eliminates all restrictions on Z, sorry. They're kind of similar. All restrictions on the Z component. All right. So what we're going to end up with is just this equation here. So the r squared equals x minus a squared plus y minus b quantity squared. So in 3 dimensions, even though we don't have this Z component, no restrictions on the Z anymore, what this is actually, so in 3D space, this represents the equation for what's called a right circular cylinder. And I'll show you how it is. So this basically, like I said, because there's no restriction on Z, all we have are restrictions on X and Y now. Okay. So this is, and I should say of radius R, right? Because our radius is just sitting there, radius capital R. Okay, so what it's going to look like is this. So we're in 3 dimensions. Okay, so here's our X, our Y, and our Z. So what this is that we have centered at AB still, but now we have centered at not at ABC, but AB0, because there is no C there to even go off of, right? So we're just going to assume that the Z coordinate is 0 because it disappeared. So here's our center, AB, all right? And we have some circle sitting on the XY plane because we don't know what to do with the Z right now. So we have this circle here, radius R, right? So, but in 3 dimensions, normally this would just be a 2-dimensional equation, but if they forced you to put it into 3 dimensions, what you would do, because there is no restriction on Z, is just extend the lines upward. Sorry, that kind of coincided with the Z-axis. Upward and downward, okay? Or you could do like dotted lines, whichever you prefer. And this becomes a cylinder, okay? So what you're going to have is like this circle replicated, going up, going down. It doesn't matter because there's no restriction on Z. You can go up or down. The circle just kind of migrates up and down, all right? So again, like I said, if you're just in XY plane though, let's say, so we have X and Y. Let's say this is AB. It's not necessarily at the origin or anything, but here's AB, then you just have a circle, right? because we don't have a z component, so it's just flattened onto the xy plane. Okay, so now for the actual like vectors. So vectors, now we're working with them in 3 dimensions, okay? So vectors in 3D. So it's kind of going to be the same thing, basically. It's just you add on this third component here, okay, this z component. Again, vectors in any dimension have direction and magnitude, or magnitude and direction. Direction and magnitude, there we go, magnitude, right? So, let's see, again, in 3 dimensions, it kind of works the same way as in 2 dimensions, just we have an added dimension. Okay, so let's say we have to calculate the components of a vector v given by connecting p to q. Then let's say p is this point, e1, f1, okay? And q is d2, e2, and f2. Then we would just do the same thing as we've done before and just add on that extra component. So we're going to take the components of the end point and subtract from them the components of the start point. So we'll have like d2 minus d1, comma, e2 minus e1, comma, and f2 minus f1. Okay? So those will give you your components there. And then the other thing is just finding the magnitude. Again, it's the same thing. Same process. You're going to take each component of our vector, square them separately. Okay? So take each component, square them separately, and here's the last one. We're going to add them together, and we're going to put them under the square root sign. Okay? And then also, just a last note on the vectors here, algebra. So working with the algebra is the same as in 2D. Okay? So basically what that means is that scalar multiplication is going to be the same. So if we were to do that, then it would just be times a, b, c, okay? And then the lambda would just factor in to each of those. Okay, so then we get something, I'll write up here. Lambda a, comma, lambda b, sorry this is so small, lambda c. I kind of just wanted to fit all the vector stuff on one slide. And the last thing is just that the unit vector, again, this is going to be the same exact thing as in 2D. If you have a vector and you want to make it a unit vector, you just divide it by its magnitude. Okay? Alright, so now on to the next thing. Okay, so here we have some new material, and the title of it is going to be Parametric Equations, I'll abbreviate, Equations of a Line. Okay, so I'm pretty sure all of us at this point have worked with lines before, in the two-dimensional case anyways, like the y equals mx plus b thing, right? But now what we're going to do is introduce a different way to name lines, and a way to even name lines in 3 dimensions, okay? So let's say we're in 3 dimensions, okay? So here's our x, y, and z axes. And let's say we know of a vector called v, all right? So here's v, and v is given by a, b, c. Those are its directions, okay? And I want you to look here. So remember before how we've gone over scalar multiples, and we said that scalar multiples, if the lambda, if the scalar value is positive, it's going to point in the same direction. It just might be longer, it might be shorter, whatever, but it'll point in the same direction. And if it is negative, then it'll point in the opposite direction, but it'll still lie on the same line, right? So all of these are scalar multiples of v, okay? And all of these put together form a line, right? It's kind of going to infinity, basically. So any scalar multiples of v will form this line here, okay? Positive going in this direction, and if lambda is negative, it goes in this direction, okay? So this gives us something important, right? So what we actually have, I'll call it r of t, and this is a vector equation here. This is going to kind of parameterize our line. That's what it's called. So r of t is this line. That's what I'm pointing to here. So this entire line is called r of t. And it'll be, instead of using lambda, since we're putting it in like function form, I'm going to put a t here instead of the lambda, okay? So this is our variable. and it is a scalar quantity, so it's a real number, okay? Like I said, it's kind of just replacing our lambda that we had before. It's kind of like lambda. There we go. Okay, so if v was ABC, then we have that r of t equals t times ABC, okay? And if you want to rewrite it one more time, then we can distribute the t inside, so then we have t times A, t times B, and t times C. Okay, so this here, everything, either way you want to write it, this is called the vector parameterization of a line through the origin. Okay, and this is an important point to note. So it is through the origin because if t equals 0, then our point is 0, 0, 0, right? So we can hit the origin by just setting t equal to 0, okay? If t equals any other value, like for example, if we wanted to hit this point up here, we can't really do that given our equation because it's not on the line at all, right? It's kind of just out there. But I will go over on the next slide what happens if you don't want a line through the origin, but you want it through this point up here, okay?